So in the morning, we have done a little bit about the magnitude estimation from the recorded data, and I have shown you how to do that. And today, in this class, we will be try to estimate the ground motion parameters of the recorded data. So, what are the different parameters which are of seismological and engineering interest that we will be finding out? Okay, and how to calculate that. I will give you a theoretical basis of that, and then in one of your tutorial class, we will be giving you the recorded time history, and you need to calculate all the ground motion parameters and see how you have learned that how to do these things. Okay, so this is one of the most important things, because after you record a big earthquake, or might be a very destructive earthquake, we need to know what are the different properties of that earthquake, and what are the different properties of the ground motions that we can find it out. Okay, so that's the estimation of ground motion parameters. But before doing that, we need to understand that what we are recording and how we are recording that. So, first of all, the strong ground motion measurements, we have basically two categories. One is the seismogram and other is the accelerographs, right? So seismographs are basically the weak ground motions, right? So we have two types of ground motion we usually define in our the community, a seismic community. One is the weak motion recording. The weak motion means it's basically the velocity sensor. So that means sensor we used are the velocity sensors. So that is what we are basically measuring, a velocity of the ground. That means, and this is a weak because the it's mostly dealing with the earthquake which are not a big magnitude earthquakes. Because if a big magnitude earthquake took place, then the velocity sensors will not be sufficient, and we need to have an accelerometer for that accelegraph. So if it is of engineering interest, then the accelerogram is basically required, and that is what we call it as a strong motion equipment. So weak motion is a seismogram, or it's a velocity sensors, and they basically used for earthquake location type of problems. They are basically used to calculate the source mechanism of an earthquake. So that means by seeing their polarity, we can calculate what type of fault plane or what type of faulting has been taken place. So from that type of record, okay, and also the seismic wave propagation. So these are basically the weak motion sensors are basically used. Now there is a strong motion measurement, which is basically uses the accelerogram, or we call it as a strong ground motions. And why it is required? Because the acceleration is closely related to the inertia. You know the inertia, right? So what is the inertia? If I was
just until I'm continuous with other prediction. But I do not belong to me. Without
angular velocity.
huh? Usually that should be spent everybody wants
In the same state of rest as the motions, right? and that is your inertia, and that inertia is equals to the basically it is related with the mass of the system, or the mass of the rigid body, right? So that's your inertia. So this inertia force is basically the mass into accelerations, right? So that's your F equals to ma. So that is equals to what we call it as the inertial force. So that inertial force are basically required for the estimation for the any structure, any the structures means is the building on the bridges. So that we need to understand how it will affect a structure, right? So therefore, acceleration, if we can get so mass into acceleration, we can calculate the force it put- it gives to the structures, right? So so acceleration based sensor, which is called as accelerogram, we are which it can be readily manufactured, because the manufacturing wise it will be much easy to do, and so from that acceleration data we can calculate also the ground velocity and also the ground displacement by doing the integration as we have done it, as we when you have discussed it last time, right? So that is what we have to do. So now, so for the engineering community, they all use the accelerometer or accelegraph at the time for their engineering work, right? Now, earlier instrument was basically the analog instrument. So analog instrument means it is the analog strong motion recorders or strong motion accelerometer. So this is called SMA. Analog SMA was there, but nowadays that all the analog records are gradually being replaced. Even in India, we are gradually replacing with your digital accelerometer, right? Because of the obvious reason, because the accelerometer, the analog accelerometer is very difficult to process. Afterwards, the processing for the data, because you have to digitize it manually, because this is being recorded, and then we have to digitize it each and every millisecond interval. It will be a tremendous task. So nowadays all the strong motion accelerometer are basically the digital accelerometer. So we need to know that this analog accelerometer once upon a time exist. Okay, so the deficiency of this accelerometer is this, that as I said, that it is a very difficult to digitize, and so if you see any record of the analog accelerometer once upon a time, this accelerometer looks like a looks like it's if it is an accelerometer, then the sensors will be the recording will be like this. So this is all the curved part, and then we have to make it a straight, and then we have to digitize it by putting a strip, and it will be very difficult. So that's why earlier accelerometers or an analog accelerometer not recorded continuously. So they were made to record whenever there will be a certain exceedance of the ground motion. So basically, what we call it as an exceedance of threshold. So in order to avoid unnecessary work, they do not allow the film to come out from the recording, because unnecessarily, if we take out the record, then you process it, and that data we do not need to do the work. So basically, they will keep it, and they put the threshold level something around, say, suppose 100 centimeter per second square acceleration, If it happens, then only you record it. Otherwise, don't record. Okay. So that is called threshold level type of detection. It was done. And then if it is if it is a very strong earthquake, then that will be recording, and then they take out that claim recorder, process it, and then do a correction from this one. But we have to make it a corrections like this. Okay, so it will all make a straight like thing, and then we put a very a strip and read each and every value in the second interval or the millisecond interval, whatever you need. But it's a very difficult operation, first of all. The second is this, that often, because since it's a manual or it's an analog recording, and it is being limited by the width of the film it has been inside, right? So if your recording things are basically giving a more motion, then it got clipped. So you will be seeing ultimately the things like this. Okay, so that does not make any sense for the wave understanding. So there is a clipped motion. So in order to have a clipped motion, if it is a very near and very strong earthquake, then might be they have a clipping occurs. So although in an accelerometer it is a very difficult to have the clip, but if it is a strong earthquake of that nature, then might be it can get also clipped. So these are the difficulties with the strong motion analog recorder. So gradually with the digital record available, it is gradually replacing the digital instrument. Now the digital accelerometer has a wide range of frequency and amplitude, and have a significantly improved accuracy, and capable of record several seconds prior to the arrival of the seismic wave. So that means here what we do in case of your digital record, we always give, say suppose this is your P wave arrival, and then there is a S wave arrival, and then all the other phases that come. So we need to define a threshold value. So let's see, I give a threshold value from here or any level. So, but any value you can give as a threshold. Let's see. I can give a threshold like this. Okay. So from this, the digital record has a memory, right? So it was when it was recording this one, and then but it has not been given the output, right? So it is giving here, and then it exceeds at this point. It exceeds the values, right? It exceeds the motion, and as soon as it exceeds, it keeps the memory, whatever the user can set. So that means might be the 60 second before the memory. So that means it will be start now sending you the data to the output from 60 seconds prior to the this triggered level, right? And so that is your post event memory, and then from there it will also take, say, something around, let us see, 80 seconds of the record, right? So that means that will be the if it is not being triggered, so after the last trigger, it will record 80 seconds. So total length of the record is basically 140 seconds, right? So that is what you have to put it into the accelerometer as a parameter setting, and that will gives you enough time series where you can successfully get the P wave and also the S wave and also the after the surface wave and including the coda. Now, yeah, please.
Sorry. I have two questions.
Yeah.
As for thoughts, I saw that why many times were matter as to how good data whereas PVP at the post website to make him market. And so so why we need estimate the same loss with that. Again, it is being break as we capable of recording several seconds prior to the L06 campaigns. And so have you told the accelerators are just working the trigger? No. That's right. And at the same time, you're actually like it can record being both before 6 seconds. It might get the start recording before 16 seconds, the arrival of the mail. Okay, so how it gets event before second second.
No, it's keep it the data in the memory. It is not outputting the things. Right. So basically whenever it's go on a recording, but it has not been triggered. So as soon as it gets triggered, because it comes the triggered level, then they take that time and in the parameter setting, you have already said, say 60 seconds before the triggering, you should also give me the record. So it will now go to the memory and bring that 60-second record, and then from the triggered level, they will also produce another 80 seconds. It will go on recording. So that means 140-second record. It will done for a single triggered level. But it might be also happen that if this is a triggered level, and then this is their amplitude, and then when it has crossed the triggered level several times, so that means it has been touched here, so they will go 60 seconds from here. But if had been last triggered is here, so from here it will be taking 80 seconds from that side. So that means it could be 140 minimum, but it could be 160 or 180 seconds also, depending upon how many times it get triggered.
So it's like manual window we are, it's like manual window we are setting. We can also keep the let's say it's 60 seconds, so we can also move it for 100 seconds.
Yeah,
the manual thing.
Yeah, but it's a parameter setting you have to do before you start recording. That is the parameter you have to set.
If we will be confused or that the capable of recording several settings I do that I was setting.
Right. So basically, if you go 60 seconds beyond, that it might be you have crossed the P wave, also you have recorded the thing. But if you say I require only 10 seconds, so might be the P wave you're not able to record. Right. So basically you have to be in the place where your seismic zones are there, and from where you are trying to get the record, you need to see what is your S minus P, the time difference expected. So if you need the full waveform from the P wave to the entire coda, then you should set it accordingly. Okay, but otherwise you will only get tricked when the trigger, the S wave will come. So your record will look like a little bit incomplete type. But all the phases will not be recorded, right? So that's the advantage. You can set it of your own. So that's the advantage of the digital things, right? So it can record, although it get triggered by the S wave, but from the pre-event memory, you can also record the P wave values, okay, or the P wave arrival time. So that's your advantage of the digital strong motion part. Okay, next, the digital accelerometer is an inertial accelerometer. So it has basically all the accelerometers, all the seismic sensors are a mass spring type of basically the system. So there is a mass, there is a spring, and but these things are attached with the ground, right? So if that frame which is attached with the ground, if there is a ground motion, then that frame will vibrate, right? That definitely, and then the system will also vibrate, but this scale will also have a motion. So then you cannot measure, or you cannot do the actual ground motion. You will be always making the relative ground motion, because everybody is basically shaking, right? So in order to avoid that, we want that the things, it can only vibrate this one, but the mass should not move. So that is what we like to have, so that we can measure the actual acceleration of the ground, right? So yes. So this is a single degree of freedom type of instrument. So that means one-dimensional motion. It will vibrate. So basically, it will have a north-south, east-to-west, and there is a vertical one. Each one is a single degree of freedom. So basically, we are measuring each sensor in a different directions, right? So what I want, that basically the mass should not move, but since the frame is moving, and that will creates the movement, and we can measure the accelerations. Now, how to do that? We had a system which we call it as a force balanced accelerometer. Force balanced accelerometer means basically what has happened, if as per the Lenge's law, there is a mass, and then there is a spring, and then there is a current is induced here, right? So this current is measured over this resistance, right? Now, since this electrical circuit, if the mass moves, then there is a electromotive force is basically developed due to the electromagnetic induction, and as a result, there will be a current flows, right? So this current across the resistance, it gives a voltage, and that voltage you measure, right? So, and then what has happened, the system, or in the force balance accelerometer, there is a feedback circuit in which the current is sent back to this wire in opposite direction, and as a result, that the mass will not able to move, or it will be immediately bring it in static conditions, and that will allow, if the mass will not move, then that frame movement can register the voltage, and that voltage is actually being measured as an accelerometer, and that can be calibrated as a ground accelerometer, right? So this current, so basically there is a displacement transducer which produces a voltage across the resistor, and the current is then sent back to this coil via a feedback circuit, and which opposes the motion of the mass with respect to the frame, right? And thus this current which is being sent is proportional to the ground acceleration. So we measure the current, and hence the voltage across the resistor, and that will be basically the ground acceleration. So this is what we call it as a FBA principle. Most of the accelerometer which is currently are being manufactured are all FBA type of accelerometer. So if you see a accelerometer in the market, if you go there to purchase an accelerometer, always try to purchase an FBA accelerometer, because that will be accurate in measuring the ground accelerations, right? So, and it has a very high dynamic range, and it will be very faithfully record the ground accelerations, right? Okay. Now whenever we have each the accelerometer, as I told you, they have three types of sensor. One sensor, when they record the vertical motion, so it is when oriented in that manner. One is a north-south sensor, and one is a east-west sensor. So these three component sensors are basically measures the total ground motions, right? Okay. Now the so this is your sensor part. Then there is a recorder part which will record the 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 data and then do a little bit initial processing and then put it into the output as your digital data. So the sensor will only sense the ground motions, take the electric voltage and send it to the recorder, and then the recorder will take the data, process it, and then it will be ultimately put it onto a format that you want it. So that format we'll be discussing afterwards. But so the recorder part is to record and do the initial processing, including the filtering and all these things. So that will be done. So earlier, analog sensors which have an analog record, which are basically the pre-1980, mostly the after 1980, in the United States at least, the digital accelerogram already arrived. In India, we had got something around the end of the 80s, so around or the early beginning of 90s, we have the digital recorders. But in US, mostly after 80, we have all the recording system. So the recording system in the analog things is basically pen, stylus, and then there is a reflective mirror and a paper or a photographic film. So what has happened, if you have done your physics experiment of the galvanometer type of experiment, where there is a light rays are being gone, and that light rays are basically moving on a scale, and that light rays are there, and the photographic plate is there. If there is an earthquake, the stylus will move the things, and it's scratch, and then the photographic plate is coming out, and the photographic plate has to be developed, and then we can get the recorded data, right? So these are the disadvantage is that basically the digitization process, and then there is a lots of noise comes into the pictures, and these are unnecessarily, we cannot do anything during the time of the analog record. Now in a digital record, we can do the filtering process, and it will be coming as a filtered data. So so in the modern digital MPA type of recorders, we have a 200 to 1,000 samples per second we can calculate. So that means each second we have a 250 samples to the 1,000 samples. Whatever you want, we can set it up. So that means your parameter setting, you can do as many as large sample as you want. You can set it up, but it also at the cost of your computer memory. So if you do not need that much of accurate sampling, then you can always reduce it. In general, 200 samples for a engineering purpose is more than sufficient. Somebody can also do it with 100 samples per second. So 100 samples per second means what? So 100 samples per second means?
in 1 second, but there are hundreds of samples and for hundreds of samples are there for in the selling point of it, but it how to say going to add when the wash by within
millisecond, right? So 1 by 100 second means it is equals to how much? 0.00? Sorry, 0.01, right?
1
Huh?
it's like 1
0.01, right? 100 means 0.01, right? So that's your take. So that's samples. That's that many of samples. But so that means each sample. So that means when if we have this type of sensor, so this sample and then these samples, if we can sampling it, so this is equals to 0.01 second, right? So that's your time. So each 0.01 second, we have a samples, right? So we can do that. So this is your sample. So you can decide your sampling interval based on your recording urgency or the recording objectives, right? And it has a very wide dynamic range of a 50 to 100 hertz is their dynamic values, and currently nowadays with the availability of a very good data communication port, or might be the digital transmission over the over the internet and all these things, we even do not do the basically the threshold recording. We allow the record to go, and continuously it will record, and then we can download the entire time. So whenever you want, you can always chop up and take the recording. So this is what we call it as a continuous data streaming. So nowadays accelerometers are capable of doing a continuous data streaming, and that continuous data will be transmitted via internet port to the recording stations, or might be the observatory, and they can see a continuous data 24/7. So every time the data is basically available, if you want some portion of the data, you can give a command, they will chop it off and give the time series data as it is required. So that's a so now nowadays, with the advantage of the digitization and also the telecommunication things or the communication port, we have a lot of luxury to get the data. Okay, so this is and the digital record is always, you can set up a noise level, and that will basically help you to filter out the noise before it gets recorded, right? Say, and this, due to the construction or the calibration and all these things, the nowadays the digital sensors along with the recorders is not more than $5,000 to $6,000 So it is very easy. Earlier, we have to spend something around $10,000 to $15,000 to get a accelerometer, but nowadays with the recorders, something else, because each sensor, each component is $1,000, and then we have a $5,000 type of seismic recorders. So it is as simple as that currently, right? So the strong motion data processing. So first of all, after you get the data in a strong motion record, we are interested to calculate the true ground motions, right? And also we try to understand what are the noises associated in the record, because if it is a continuous streaming, there will be always some noise is when it coming, right? So this noise level you can analyze. So what is your noise level before the P wave comes, and then we can see the record. So this noise level, what we call it as a pre-event noise. So before the event appears, the pre-event noise is the noise level of that particular site. So that noise is due to the site phenomena, due to the cultural noise, or any other traffic noise, or any other noise in an urban setup. That is the pre-event noise. So that noise, we need to separate it out from the actual event data, right? So that's the actual event. So this is what we call it as a signal. We call it as a signal because that is what we are interested in. And this is your noise. So signal to noise ratio improvement is a very important task for getting a good quality of the data. So data quality we need to talk about, and the data quality is basically the signal to noise ratio. Okay, so data quality is basically the signal to noise this ratio, or we call it in some way rather, we take the frequency spectrum or the full Fourier spectrum of the pre or the signal part, and the Fourier spectrum of the noise part, and calculate the signal to noise spectral ratio and try to see whether it is how big is the noise level with respect to the signal level or the amplitude level, and then we can find out whether that data is a good quality or the bad quality. If the noise is comparable to the signal, then definitely it is not a good quality of the data. We require the signal level at least 3 times to the noise level to qualify that record as a good signal to noise ratio record. Okay, so that signal to noise ratio we have to calculate in order to understand the quality of the data. Now, our next part is basically the processing of the data. Now, before you start recording, you need to decide on your sampling intervals, right? So that whatever I have told you, so that's your sample intervals. And if you, in general, we will be using the delta t, or the sample interval is equals to say 0.005, right? So this much of, or this is called this much of second, or it is called 5 millisecond sampling interval. This is usually a strong motion record. We use that. Okay, so that will be equals to how much? So 1 by delta t will be equals to 1 by 0.005, right? So that will be equals to how much? 1000 divided by 5, right? So 200 hertz. Okay, so 1 by t, 1 by delta t is basically equals to the delta f, right? So it's a 200 hertz frequency. If I get that, so then it will be the 200 hertz. So if you sample it at a 0.005 second, then you will be getting your Nyquist frequency. It's basically half of that, right? So the 200 hertz divided by 2, so that means 100 hertz, right? So if you do the analysis of a time series which is sampled at a 0.005 second or 5 millisecond interval, the maximum frequency you can get the information is around 100 hertz. You cannot get any information of signal which has a frequency 150 hertz or basically the 120 hertz. So you cannot get, because that is due to the Nyquist frequency. And I think in your digital signal processing, you have understood what is the Nyquist frequency is. And so what is the Nyquist frequency? It is called another name. It is called Nyquist frequency has another name. It is called in your seismic exploration also, we need to be sure on that, right? So that is called folding frequency, because after each 100 hertz, the values are being folded, right? So if you do the Fourier transform, it will be all basically the folded. So after 100 hertz, whatever you get in 120 hertz is basically the replica of the 20 hertz frequency, or might be the 150 hertz is basically the 50 hertz frequency. So everything will be basically replicated after the Nyquist frequency. So the maximum frequency you can get to use it is basically the Nyquist frequency, which is 1/2 delta t, right? So if you want to explore the frequency content of 150 hertz, then you have to have a frequency sampling of greater than 150. So that means your 1/2 delta t has to be equals to, therefore, the, say, suppose 150 hertz. So you calculate what should be my delta t values. So 1/300 will be the things, and then that you can calculate based on this, right? So you cannot expect to sample at 0.005 second and try to retain or try to have a information extracted out from that signal, which is 100 or greater than 100 hertz, right? So that you have to first decide what you need. Okay, so we also need to know the instrument response of during the analog